So I shall now discuss diagrammatics for generating functional. Having discussed the form of the generating functional and the relation between connected and disconnected diagrams, this is now we are going to look at the various terms of the generating functional, both connected and disconnected, in terms of diagrams. And since we know the Feynman rules, we can get expressions for any of these terms once I know the diagram. So that's what we are going to do. So So we write W tilde J as W tilde 0 times Wj, where Wj is the generating functional for Green's function. And this Wj has non-vacuum diagrams, and it has a form exponential of z of j, non-vacuum diagrams, but both connected and disconnected. And it has a form exponential z of j, where z is only connected non-vacuum diagrams. This, on the other hand, has vacuum diagrams, and this can also be written as exponential z tilde of 0, where z tilde has only connected vacuum diagrams. So we shall now write down the contributions to z tilde 0, zj, and wj in terms of diagrams. So let me start with z tilde 0. Z tilde 0 are all vacuum diagrams connected. So we have already discussed that first vacuum diagram, leading order, which is quadratic in vertices, which is quadratic in G, and at the same level, G square level, we have another diagram. And there will be higher order terms. Zj does not have any vacuum diagrams, because if you set j equal to 0 on both sides, you see w tilde 0, and this w tilde 0 will cancel, implying that w of 0 is 1, and therefore that is exponential z, and therefore z must be 0. When j equal to 0, z must be 0. So there is no vacuum diagram contribution to z. So it starts with 1 point, linear in j terms. So the linear in j terms we had discussed earlier, there is no way you can have a tree-level diagram which is linear in j. So you start with a loop diagram like this. And then this is order g, and then you have order g cube, this term, and so on. We shall discuss this significance of this not having a tree-level diagram later on, but from diagrammatics, topologically, we see that there's no way you can draw a single dot diagram using 3 vertices. Then you have quadratic in J terms, and the first term is the free propagator, which we saw in W0, W0 of J, like free theory generating functional. And then next the vertex corrections. You have we saw that we should have at least two vertices in order to have so you cannot have a single vertex correction to order G correction to the 2-point function. It's not a 2-point function, it's a quadratic in J term in ZJ. So remember, this is not a Green's function. These points are not fixed in space time, but they are all integrated over. They are these J factors which are integrated over, and they are indistinguishable. And the next term will be at the same order, quadratic in J. There is another diagram, which is this, and so on. And then at a cubic level, there is a tree diagram, which is basically the primitive vertex. And then next diagram comes with 3 vertex corrections. Then there is a diagram which is given by this plus these are all G cube contributions to the 3 J cube term, and then there are higher order in V or G. Now the Feynman, if you use the Feynman rules for each one of them, you can get the corresponding mathematical expression. But then in the Feynman rule, you have to multiply by the 1/s symmetry factor, and that you have to find out. Feynman rule does not tell you what the symmetry factor is. It is you have to find out, and we discussed a few methods of doing so. One method, I'm going to use it quickly to get the values of A's quickly for this diagram. So I'm going to use the symmetry method. Okay, so if you do the symmetry methods, then okay, so I did not keep space here. Let me get more space here. So for this diagram, we already discussed, sorry, so we don't need this, because for this diagram, we already discussed the symmetry factors for the vacuum diagrams. Let me discuss. So in ZJ, there will be higher higher powers of J terms, of course, and then let me discuss symmetry factor here. So symmetry factor is, as you remember, is related to the symmetries. And we discussed that this has a symmetry if you look at the orientation reversing. Or in other words, you are flipping this loop, twisting the loop. So that is a factor of 2. So that's so S is 2. In this case, you have 2 vertices here. So these 2 vertices can be interchanged in a symmetry transformation. Not only that, these 2 links can also be interchanged between themselves. So this is S equal to 2 square. So one factor of 2 is coming from the interchange of the 2 vertices, and the other coming from the interchange of these 2 propagators. This one is S equal to 2. We discussed this many times before, interchange between the 2 dots. Here you have interchange between the 2 dots, and then interchange between these 2 links, these two links. So this is also 2 square. Here again, you have interchange between the 2 dots, and just like this one has a has a twofold symmetry. This one also has a twofold symmetry. So that's an additional factor of 2, which is 2 square. S is equal to 2 square. Here S will be factorial 3. We know that is there in the factor of in the primitive vertex itself, G by factorial 3. That's factorial 3 exactly cancels this one, and that same origin factorial 3. It's just a interchange among the 3 dots. Here you see this interchange among the 3 dots. If you interchange, then the diagram remains symmetric. But then other than that, you do not have any other symmetries in this thing. So because none of these links can be interchanged between themselves, which you can call as symmetry. So S is equal to factorial 3 again here. Here you of course have a symmetry for interchanging these two and flipping these two lines. So that is 2 square. So S is equal to 2 square. It is same here because of the same argument, to interchange between the 2 dots and then twist this loop. So this is how. So you can calculate the symmetry factors by looking at the symmetries of the diagram, and then the Feynman rules. You use them to get the expression for each of the terms. So Zj will be sum of all these terms and many more, infinite number of terms. Now, if you want to calculate Wj will start with 1, because as I just discussed, j equal to 0, w equal to 1, and then sum over n greater than or equal to 1, n being so then it's an exponential of z, exponential of this which you are writing. So this entire thing, whatever you have for z, all terms, entire thing sits in here within this bracket. So that would be this plus this and so on, all to the power n. That's the exponential. Now exponential has e to the power x has a sum over n, x to the power n by factorial n. That 1 over factorial n is actually a symmetry factor, and I'm taking the convention that the diagram includes all the symmetry factors in it, and just like this diagram has its symmetry factor within itself. So I'm not writing 1 over factorial 3 outside. The Feynman diagram says that you have to multiply by 1 over factorial 1 over s factor. So I'm not writing 1 over s. If I write, would be writing 1 over s factor outside for every term, then the Feynman rules will not have a symmetry factor. But while writing these terms, sum of these terms in Z, you need to figure out those factors in each case. It's not, it's just a convention. Either you could write the symmetry factors outside the diagram, in which case Feynman rules will not have the last rule that multiply the overall by the overall symmetry factor, because it's already there. It is the method of expanding Zj. That method itself tells you that there is a relative strength for each one diagrams, which is given by the symmetry factor. But we are not taking that convention. We're taking the convention. We are just adding the diagrams, each with relative strength 1. But within the diagram, we have the symmetry factor sitting inside, and therefore the symmetry factor is there in the Feynman rule. So taking the same convention, this entire infinite sum is a diagram. When you add them, is a diagram. Okay. When you add 2 diagrams, that's another diagram. So this entire thing to the power n, that's also a diagram. So the whole term is a diagram. And in the Feynman rule, if you want to keep that rule that you multiply by the symmetry factor, then when you write Feynman rule for this, entire diagram, it will have a one over factorial and additional symmetry factor in addition to the individual symmetry factors that they have, which I have written here. This power of to the power n, because of the n identical factors we discussed in detail, it will have an additional symmetry factor 1 over factorial n. So that is the convention that I'm choosing here. It's just a convention. You could write 1 over factorial n, then you have to say that for disconnected diagrams, I'm taking a different convention where I write 1 over factorial n separately, explicitly outside. So this has a symmetry factor factorial n. Now then you have to binomially expand the entire thing to get wj. If you want to get individual terms of wj, you have to binomially expand these, and all powers and combinations will appear there. Like one term will be this to the power n so you have to do a linear binomial expand the entire series and get individual terms. For example, one term will be this to the power n, and that term will have a symmetry factor, of course, 1 over factorial n times that individual diagram. This has n copies. This is n copies of the same diagram. It's a disconnected diagram. So this diagram will have a symmetry factor, symmetry factor 1 over s, where s is equal to the symmetry factor of this individual piece, and then then the factorial n, because there are n copies, and symmetry factor for this individual piece we have discussed is 2. So this is s equal to 2 times factorial n. Similarly, there will be another diagram, just randomly picking some examples. There will be another term which will be this. Like all sorts of combinations you will get from this exponential expansion. This is linear in this and quadratic in this. So you could ask what would be the symmetry factor for this term, and then you can calculate symmetry factor for this individual term, then this individual term times 2 because of the second power, because there are 2 of them, and therefore permutation symmetry of that. So this is 2, and then this diagram has we have seen is 2 square, and then another 2 because it has a power 2. We can see this diagram is 2 square, s equal to 2 square. So that is the total. So this is one way of seeing getting the symmetry factor, just by applying our methodology of the symmetries. Another way of looking at it, to check consistency, one should be able to see that we know that the entire diagram has 1 over factorial n, and then you just do binomial expansion and figure out what is the coefficient of this term. So if you do binomial expansion, then you could have to ask from where this term will be coming. This term is a cubic term because this is 1 power, this is 2 power. So it is this plus this to the power 3. It is this expansion will give this. And if you do that calculation, because this plus this to the power 3 will come. So if you take this n equal to 3 terms, so all these diagram to the power 3, then you take these as say a and everything else to be b, then it is a plus b to the power 3, and that has a first term is a cube. This a cube will have this to the power 3, and it is that term that is it is sitting inside that term. Now if you take this plus this diagram to the power 3, then there'll be now let me call this as a small a and this is small b, then it is a cube plus b cube plus 3a square b plus 3ab square. So this will give 3ab square. So 3 times this times this is what this diagram is. And in front of it, because of this power 3, there is a symmetry factor of factorial n, so this is by factorial 3. And then that gives you basically this factor is nothing but half. This is basically, so a is equal to 2. This 2 is this 2. So this is an overall factor, but then there are individual symmetry factors which are 2 and 2 square, and this is 2, which is basically, which corresponds to this 3 by factorial 3. See, 3 is coming because of the binomial expansion, and this factorial 3 is coming because of the power cubic term, because of the power. So then this is the additional overall factor of half multiplied by multiplying the entire diagram, and the individual piece will have their individual symmetry factors, and therefore it will be 1 over 2 times the individual symmetry factors, and that is precisely this result. Okay, so you can check it that way, whether the result is right or not. So this is all I wanted to say about the diagrammatics of the generating functional. Next job will be to move into the diagrammatics for the Green's function, which is the goal, which was the goal, original goal, to calculate the Green's function. So let me start that discussion. Diagrammatics. So Gn of x1 to xn is given by del I del j x1 to del I del j xn wj at j equal to 0. And if you, this is a generating, this is the Green's function, and this Green's function is not only connected, it has also disconnected pieces. So if you calculate connected Green's function, then it will be given by this. So you remember that in the free theory we had only one connected diagram, which was given by this one, and but the Green's function had many other terms which are corresponding to the multiple copies of the same. So those are like GNs, but G connected n, there is only one possible Green's function, which is a 2-point function. That was the scenario in free theory, but now structure will be much more complex. We will have many more diagrams in the connected, and then many other, because this has disconnected, many other variants here as well. So let us see how from the expansion of Z, diagrammatic expansion of Z, we can calculate the connected Green's functions, because disconnected is not very interesting, because they are just multiplication of the connected ones. So I'm going to discuss the connected Green's function. So let us begin with the simplest the simplest one. So that is n equal to 1 connected x. So this is del I according to this definition applied on that entire sum that we have drawn in the previous page. This is a j to the power 1 terms, then j to the power 2 terms, and so on. And of course, j to the power 3 and all the other higher order terms. But then finally, after taking the derivative, you have to set j equal to 0. And of course, this will all be 0. The quadratic and all higher powers of j terms will be 0 because there is only single derivative. And this single derivative will give only non-zero result working on this first line, acting on this first line. So and when it acts on a particular term in the first line is just, so this in the if you remember the Feynman rule for the dot is a factor of I times j, where the j is integrated over. So that integrated over the whole space time. Now you are taking a derivative at particular jx, so that will involve, that will absorb that j factor and make this point not a dot but a fixed, which we will call external point, that we will denote by a cross, which means that is an external point, that's a fixed point that is not integrated over. So what you will get is this. And this cross is obviously the label x that appears here. This is x. Now you see this for these diagrams, the symmetry factor does not change for these diagrams because there was only a single dot and there was no symmetry factor associated to that, and fixing that dot to a particular space-time point does not change the symmetry. The symmetry factors in this diagram will remain the same. But we will see how the symmetry factors change for other diagrams. But before that, let us write down the Feynman rules. We have understood the calculations. If you take higher derivatives, you will simply be acting those derivatives on higher powers of j terms and so on. So, and each time that the derivative hits a point, it fixes to an external point, and no other changes happening. No other changes are happening here except for possible changes in the symmetry factor. The symmetry factor that I had here can change. For example, in this case, if it has 2 points, it has a symmetry factor 1/2, and but then this term will give you a g2 will have 2 derivatives, and that will act on that, and because of the interchange, and these 2 derivatives can act on these 2 points in 2 ways. That will cancel that factor of half. So symmetry factor changes, it becomes 1. So I will discuss it in more detail later on, but let me write down the Feynman rules. So Feynman rules is draw all possible topologically distinct diagrams using crosses, which are external points, propagators, and vertices. Draw all possible topologically distinct diagrams using crosses, which are the external points, propagators, and vertices. And then for each external point, write a factor of 1. For each vertex, write I times g times an integral over the location of the vertex. And Number 3 is propagator. For each propagator, write 1 over I delta x minus y, and the last one is multiply by the symmetry factor. But this symmetry factor, as I discussed before, is new in general, different from that in the corresponding graph in Zj, as dots were indistinguishable in Zj, but crosses are not. So it's a new factor. Different in general from that in the corresponding graph in Zj, as dots are indistinguishable but crosses are not. So once we have this, now it is straightforward to whenever you have a diagram for a Green's function, given a diagram, it is easy, straightforward to convert that to a mathematical expression using these rules. Now let us go back to studying the diagrams again. So now 2-point function, connected 2-point function x1, x2 will be given by, just like this. You take the connected j square terms because it has 2 derivatives, and therefore cubic and higher order terms will be 0 because they will be, after the derivative, some residual j factors will remain, and after setting j equal to 0, those terms will drop. So it will only come from quadratic in j terms, which is the second line here, and then it's just converting those dots into crosses. That's the only difference. These are the 3 diagrams corresponding to these 3 terms here. Of course, these crosses are the fixed points x1 and x2. I mean that it's understood. And now let me now see what the symmetry factors are. This symmetry factor will be 1 because when we had the term in wj had dots, and that had the interchange symmetry, which gave a factor of 2 for a's. That symmetry is eliminated because these 2 points are distinguishable. Similarly, here we had 2 square interchange of the 2 dots and the interchange of these 2 lines. This remains the symmetry, but these dots become external distinguishable points. So it is only s equal to 2. And the same thing here, it is the same argument. This dot interchange symmetry is eliminated, is not there anymore, but twisting the loop is still a symmetry. So that is s equal to 2. And this is how you will get all other higher order terms, higher order in g. So this is g square, this is also g square, this is g to the power 0. So often we write this entire whole series as a complete 2-point function like this, which means given only the condition that you have 2 external points, what the entire series of diagrams, I'm not classifying them as in terms of number of vertices, You will do that when you calculate it, but when you add all of them, I'm just writing this gray box or gray blob here, because of the blob means all possible diagrams that are consistent with this configuration, that there are two external points.